Hello again, it's Ismail Badran from Najah National University again, and today we are going to start chapter 15, which is the last chapter in this course for Chemistry 101. And today we're going to talk about acid-base equilibria. So this chapter is basically based on the concepts that we discussed on chapter 13 and 14. And specifically here we're going to talk about buffers. And the definition of buffer basically is that a buffer is a solution that resists changes in pH. So that's the difference between buffer and any other solution. So if you have a buffer in the lab and if you add, let's say, an acid or a base to that, the pH wouldn't change that much. So a buffer is a solution that resists changes in pH upon the addition of small amounts of either strong acid or strong base. So basically, if you have a beaker filled with water in the lab, and let's say this water has a pH of around 7, okay? And if you add either a strong acid to this, like HCl, we're gonna see that the pH would drop significantly. So the pH will go down significantly. Like let's say the pH will go to around 1 or 2, depending on the strength of the acid or the concentration of the acid. And if you're adding NaOH to the water, the pH also will increase dramatically to around 11 or 12, whatever. But in case if you have a buffer, and this is the difference between a buffer and just regular water, if you have a buffer, and we're going to talk about the constituents of the buffer soon. If you have a buffer solution, and let's say this pH, of course you will have either acidic buffer or basic buffer. You can design a buffer to the pH you want. Let's say we have a buffer over around pH of 4. Now if you add H plus to this from HCl or a strong acid, the pH wouldn't change that much. It might decrease to 3.8 to 3.9, so that wouldn't affect the pH of the buffer significantly. Same thing if you're adding OH minus from an external source, like let's say KOH or NOH. If you're adding OH minus to that, the pH will remain the same around 4. And buffers, for example, have a significant role in chemistry and biology, and blood itself is the best example of a buffer, because blood has a pH around 7.4. If you ever done a blood test and it should say in your blood records that your pH, the blood pH is around 7.4. So increasing or decreasing the pH of that would cause a danger to the human being life. So the pH of the blood should remain roughly around that number. So what is a buffer again? What is the constituent of the buffer? The buffer, the chemical definition of buffer, a weak acid along with its conjugate base. Okay, so that's the salt of that acid. Or if you want to make a basic buffer, you can also bring a weak base like ammonia, okay, along with its conjugate acid. So an example of a weak acid would be acetic acid, CH3COH. That's gonna make you a very good buffer. But acetic acid by itself is not a buffer, by the way. It's only a weak acid, so you should bring the conjugate base. That's a salt of the acid. So I can bring a salt of that acid, so CH3CONA, sodium acetate. So that's a buffer, okay? That's a buffer combination. Another example would be, let's say, HNO2, not HNO3. HNO3 is a strong acid. You need to bring HNO2, which is a weak acid, and you can add to that KNO2, sodium potassium nitrate. So a mixture of potassium nitrate and nitrous acid would make you a good buffer. For the example of a basic buffer, you can make ammonia, but ammonia in aqueous solution is NH4OH. That's ammonium hydroxide. That's ammonia. Again, that's not a buffer. You should add to that to the salt of that weak base. So that would be, let's say, ammonium chloride or ammonium bromide or any other salt that dissolves completely into conjugation with the base. So that's a buffer chemically. And the way buffer works is actually it's based on something we call the common ion effect. Okay. So for the common ion effect, let's discuss the first case where we have a weak acid. Let's refer to the weak acid with HA, like HNO2 or HF or whatever. So that's HA. So A would be the anion. If you have a weak acid, as we learned in the previous chapter, it would dissociate partially in water to form H plus plus the A minus. So A minus here is the base. Okay, so that's your weak acid. This is the base. You will have also the salt of the acid. So let's say XA, that's a salt, but the salt will be soluble in water, so there is no need for equilibrium here. So it's going to be X plus plus A minus. So just imagine here that you have, let's say, HNO2 as a weak acid, okay? So this NO2 minus would be the A minus, okay? So A minus in this case would be the NO2 minus. And for the salt, let's imagine that you have KNO2. So again, the A minus is NO2, but the X here, the X plus would be the K plus, okay? So the X plus would be the A plus. Anyway, we're gonna talk about general here as a general concept. You see here that A minus is coming from two equations, from the first equation and the second equation. So this is what we call a common ion, because it appears in both equations. But you need to understand that this A minus is sourced mainly from the second equation, because we learned in the previous chapter that the amount of A minus and equilibrium of a weak acid is very low. It's almost 1 or 2%, because that would depend on the dissociation percentage of the HA. But for a salt, the salt is completely ionizable in water. It's completely dissociable, so that would give you a good amount of A minus. So although it's a common ion between the two equations, but the amount of A minus is mainly coming from the XA. So now let's see how would a buffer resist the changes in pH. Let's take a look at these two slides here. So first of all, we have this system as explained. The HA aqueous goes to H plus and A minus. That's the equilibrium. That's our equilibrium from the first step. We understand that we have a lot of HA. We have a little bit of H plus and a little bit of A minus from the first equation. We also have the salt, which will give us a fairly good amount of A minus. Okay. So the major species here, if you've even been asked about the major species in this system, that would be the HA. We have a lot of HA. We have also the H plus. We cannot neglect that. And we have also A minus. Now let's imagine that we have a rocket of H plus coming to this buffer system. Like we are adding a small amount of H plus from a strong acid like HCl here. That's step number 1, okay? So this is your defense system. So you're asking yourself, who's gonna defend this? Who's gonna treat this? This H plus is an acid, so we need a base. The only base that is found in the system is the A minus. A minus is your only base, and basically the A minus is coming from the salt. So this is the first step. The second step, that would be the reaction between H plus and A minus to form HA. So this will cause the A minus to decrease because you're consuming A minus. And as you learned in chapter 13, according to your electrolyte principle, if you're removing A minus from this equilibrium, that will actually affect this equilibrium. It will shift it to the right. So as you see here, the third step, the HA will ionize more to give you more A minus instead of the one that is consumed. And that will actually cause the levels of H plus to increase a little bit, causing a small changes causing a decrease in the pH. So again, briefly, H plus reacts with A minus to form HA. The disturbance here is caused by the decrease in A minus, so that will shift the equilibrium to the right. So again, here you see this arrow, the equilibrium shifts to the right, causing a small increase in the H plus, and that will cause the pH to decrease. And this is how the buffer works. For the case of OH minus, again we have the same system, nothing changes. We have a rocket of OH minus coming. That's from probably KOH or NOH. The OH minus will react with the acid. What do we have here? We have two acids, by the way. We have the H plus, which is an acid. We have also the HA as an acid. But we understand that the amount of HA is much higher than H plus. So probably this is the one that is gonna react with the OH minus. So HA reacts with OH minus as a second step to form A minus and H2O, and because HA is consumed, the reaction will shift to the left actually, causing a small decrease in the H plus and therefore an increase in the pH. For the buffer calculations, we have the Henderson-Hasselbalch equation, or in German it's Henderson-Hasselbalch equation, and we can easily derive this equation from the equilibrium of a buffer, and that will bring us to this equation: pH is equal pKa plus log A minus over HA if we have an acidic buffer. For a basic buffer, we have another equation here: a pOH is equal pKb plus log BH plus over B, where B is the base and BH plus is the conjugate acid. So this is a fairly easy equation to apply. Okay, so we have an example here, 15.4 from the book. It says calculate the pH of a solution containing 0.75 molar lactic acid. So lactic acid must be a weak acid because it's giving you the Ka here, and 0.25 sodium lactate. So that's the salt, or that's the conjugate base of the acid. Lactic acid, of course, is a common constituent of biological system. For example, it's found in milk and is also present in human muscle tissues during exertion. This question, you don't have to do a lot of calculations here. You can right away apply the Henderson-Hasselbalch equation because you have the concentrations and you have the Ka. So you can jump and say that the pH is actually equal to pKa, which is minus log the Ka of the acid, plus log concentration of A minus divided by the concentration of the acid. And I'm gonna do that right away. So it's minus log the Ka, which is been given 1.4 times 10 to the minus 4. So you need to do that separately, of course. Okay, plus log log A minus over HA. So the HA is the acid, 0.75 molar. Okay, so that's in the denominator here. And the A minus is sodium lactate, so that will give you sodium plus and the lactate ion, which is the A minus. And because it's a salt that dissolves completely in water, it should give you the same concentration. So a 0.25 molar salt will give you a 0.25 molar of also of the base. So that's ready here. You can use your calculator to do the calculations. I'm going to use Excel. So 0.25 and numerator, and you have 0.75 here. I'm going to find the ratio. So it's equal to that divided by this. I'm going to take the log of this. Okay. So this side here, this log is minus 0.477. Now minus log the Ka, I'm going to do that as well, 1.4 to the E minus 4. So minus log, that means it's equal to minus log this number. Okay, and that would be 3.8. 3.8, let's be accurate here, 54. So the answer will be 3.85 minus this number. Okay, and that will give you around 3.2 or something. It should say here 3.38. Yes, let's double check that. So equal this minus that. Yeah, so 3.38 exactly is the answer here. So that would give you I would say 3.4. So that will give you an acidic buffer. Okay, with this ratio of the buffer of the acid and the base, that will give you an acidic buffer. And by the way, if you have an equal amounts of A minus and HA, let's imagine that you have, let's say, 0.5 of this and 0.5 of that, this will be unity, because 0.5 divided by 0.5 is 1 and log 1 is 0. So in that case, this is called the 1-to-1 buffer. Okay, that's the easiest buffer ever. A 1-to-1 buffer, it has equal amounts of the acid and the base, and in that case the pH will only equal to the pKa. So that's another case of a buffer. in here you have another example where you have a basic buffer, so 0.25 molar NH3 is give you the Kb of that base, and also we have 0.4 molar of NH4Cl, and it says also calculate the pH of that solution. So let's do that again. So example 15.5. We have the first thing we have is we have NH4OH, that's your base, okay, so that's in equilibrium with its conjugate acid, the NH4 plus and the OH minus. I'm not gonna write aqueous here just for time saving. And we have also the salt NH4 plus Cl, sorry, NH4Cl, which completely dissociate into NH4 plus and the Cl minus. Right? Now, so this is your B plus. Sorry, this is your BH plus. This is the common ion, what we call the BH plus, because it's taken, and this is your base. Okay, so for NH4Cl it's 0.4 molar, and because it's completely soluble, that will also give you 0.4 molar and 0.4 molar of this Cl minus. For the base, the concentration of it, it's 0.25. So these are the two numbers that you need to apply, but you cannot use that pH is equal pKa, because he's not given. This is a basic buffer. Well, you can if you find the Ka. Let's go back here to this equation. Well, actually, you can use this equation if you find the Ka for the ammonia, and then you plug in the numbers, or you can use this equation right away, which says the POH is equal pKb plus log BH plus over B. So I'm going to use this here. So again, it says POH, not pH, is equal pKb plus log pH plus divided by the B, the base. In that case, it's going to equal to minus log. I think the Kb of ammonia is equal to the Ka of acetic acid for some reason. It's a coincidence, by the way. It's 1.8 to the minus 5. So times 10 to the minus 5. And you need to do that in separately. I think the answer is 4.77, as I remember. Plus log, now BH plus, which is the base, sorry, the conjugate acid, which is 0.4. So that's not 1-to-1 buffer. That needs some calculations. Okay, so you can find this in the calculator, and you add the numbers together, and you will find the answer to be around 9.05 or 9. So this is a basic buffer. If you want to prepare a basic buffer in the lab, you can do that. Now, you can also solve this, as I said, in different way. You can find the Ka of the ammonia, because Ka times Kb is equal Kw. So Kw is 1.0 times 10 to the minus 14. Okay, and Kb is given, so you can find the Ka, and then you can go back and say the pH is equal to pKa. You can do that, plus log A minus divided by HA. But in this case, this would be your ammonia, the base, and this would be your acid. So you need to flip them around. So try that yourself, and make sure to solve these questions. And that will be it for this chapter 15. Thank you so much for listening, and have a great day.